In our previous unit, we talked about database models or data models. So I talked about the relational model amongst many others. In this unit, we are going to concentrate on the relational model, and this is going to be our primary topic for the next 5 or 6 weeks in this course. We're going to come back to some of those other models later on when we talk about big data and things like that. So we'll revisit some of that a little bit in the future. But for right now, we're going to concentrate on these relational models, or the relational database model. So in this unit, you're going to learn about the relational database model logical view of data. We'll talk about the basic component, which are relations or tables, and that those tables are made up of tuples and attributes, or rows and columns, which we discussed before in the other unit. That relations are implemented as tables in a relational database management system. We'll learn about the database operators, the data dictionary, and the system catalog. And then we're going to talk about data redundancy and Cobb's model at the very end. So those are our basic objectives for this unit. So let's get started talking about the logical view of data. So a relational database model enables logical representation of the data and its relationships. If you recall, in our previous unit, we talked about data abstraction, or layers of abstraction with databases. The logical view is the highest level of abstraction. There's the physical layers underneath, but the logical and conceptual layers are above at the top. So that's really what we're talking about here in this unit. We're talking about that higher level of abstraction. These are the characteristics of a relational table. So in a relational database, you have tables. We're going to talk more about this in a little bit. But those tables will usually have these 8 characteristics. Number 1, a table is always 2-dimensional in a relational database. So that means it has rows and columns. You can have other dimensions in databases. When we talk about things like NoSQL and Hadoop and all those other database engines and object-oriented database engines, sometimes you have cubes, data cubes, which you can have multiple dimensions. But here, with the relational databases, nice and easy to follow and conceptualize this. We just have those 2 dimensions, which is the row and the table, or rows and columns, rather, within a table, similar to Microsoft Excel, which I've talked about before. And number 2, those tables, which are also tuples mathematically, have a single entity occurrence within the entity set. In other words, each row within a table has a single instance of an entity, is a specific entity. For example, if you had a table of students, each row in that table is an instance of a specific student. Number 3, each table column represents an attribute, and each column has a distinct name. So what that basically means is that when we have entities in this table, they all have similarly named attributes that describe those entities, and each intersection of a row and column represents a single data value. And that would be the 4th characteristic. The 5th is that all values in a column must conform to the same data format. So for example, if we have a column for student's date of birth, that would have to be a data, the data type for that column would always be a date. You couldn't put some other value in there. Some data structures that are unstructured, so some data models that are unstructured, you have some flexibility there. But with a relational database model, you're locked into a certain data type, and that really helps us with some of the integrity things that we've been talking about. The 7th characteristic is that the order of the rows and columns is immaterial to the database. And number 8, each table must have an attribute or combination of attributes that uniquely identifies each row. So to that end, let's talk about uniquely identifying each row. This is where we begin talking about keys. So keys consist of one or more attribute that determines other attributes. So a key, when you have a key attribute, other attributes follow that key, or that's how we can identify an attribute, and thus an entity, and thus all of its attributes. And that's really what they mean there. When they say that a key it consists of one or more attributes that determine other attributes, what we're saying is that all attributes can be identified by the key, thus the entity, right? The entity is nothing more than a collection of attributes. It's used to ensure that each row in a table is uniquely identifiable and to establish relationships with other tables. So it serves both of those purposes, having keys, so that we can uniquely identify a single record or a single row in our table, and so that we can reference that from other tables, which is where our relationships come from. A primary key is the attribute or combination of attributes that uniquely identifies any given row. You don't always have to have a primary key, but you'll see later on, especially in physical design, it's definitely best practice to have a primary key. Determination is basically a fancy term that talks about how keys relate to or attributes can relate to a key. So usually you have a determinant, which is basically your collection of keys, which could be a collection of attributes, and then you have dependents, which are determined by the determinant. So it's just another way of wording this. It's kind of fancy database words, but really what we're talking about here is keys. So dependencies, so a functional dependence is value of one or more attribute determines the value of one or more other attributes. And here we have the terms determinant and dependent, which I brought up in the previous slide. So the determinant is the attribute whose value determines another, and the dependent is an attribute whose value is determined by another attribute. So a dependent is determined by the determinant, basically. But again, it's just another way to word that we have a key that identifies a record, which is a collection of all of those attributes. So a composite key is when our keys, or our key that identifies a record, is made up of multiple attributes. So when you have multiple attributes to identify a record, that's considered a composite key. A key attribute is an attribute that is part of a key. So any attribute that is part of that composite key would be a key attribute. You don't always have to have composite keys. In fact, it's more common to have a single attribute that is a key. So it's both the key attribute and the primary key. And entity integrity is a condition in which each row in the table has its own unique identity. Not required for most relational database engines, but it's a good idea to conform with that rule, with the entity integrity. So null is the absence of data. Let me go back to the previous slide. So with entity integrity, all values in the primary key have to be unique, but the second requirement is that no key attribute in the primary key can contain a null value. A null value is essentially the absence of any data. Null doesn't mean that you put an empty field in or that you have a 0 or something like that. Null literally means the absence of anything. So it basically means that the column simply doesn't exist for that entity. So unlike Microsoft Excel, where you always see that column, with a database, that column doesn't necessarily have to exist for certain. You can skip that column or not have that column for certain entities. It simply doesn't exist, and that's a null. With referential integrity, every reference to an entity instance by another entity instance is valid. That's what referential integrity means. So what that means is anytime you have a reference to another table, it has to exist. So let me show you what I mean. I'm going to go forward to the next slide here. So take a look at these two tables. We have a product table at the top. And this is from your textbook, by the way. We have the product table at the top, and we have the vendor table on the bottom. All of the products have vendors. But we don't list the vendors in the product table. There would be a lot of redundancy if we did that. One of the things with relational data or relational tables is we want to reduce that redundancy. And one of the ways to do that is to reference another table. We'll talk about that in more detail with normalization later on. But taking a look at that table on the top, we reference the vendor in the other table. So look, for example, at the House Light Chainsaw, which has a 16-inch bar. It's the second item in the product table. It has a price of $189.99. You can see that the vendor code is 235. So I can look that up in the vendor table, and I see that the vendor is Henry Ortozo, and his phone number is 899-3425. So looking at that relationship, what if I had a vendor code of 247? Well, there is no vendor 247. So that would break the integrity rule because we don't have a reference to a valid vendor. So that would be a problem. And we try not to, or we try to avoid having those situations with a, in a relational database. So you can have constraints and things like that. And the relational database will automatically enforce those constraints and enforce that integrity for you. So with keys, there are different types of keys. There's a super key, which is an attribute or combination of attributes that uniquely identifies each row in a table. So once you've identified the attributes that can uniquely identify the table, now there may be more than one super key. So a candidate key is the minimal or irreducible super key, a super key that does not contain a subset of attributes that is itself a super key, so the least common denominator. And then you would take one of those and make it the primary key. So anything that is an irreducible super key can then become a primary key. You may have multiple candidate keys. For example, I might have a table that has a list of students, and there might be a social security number in there, and there might be phone numbers in there, and both of those could be candidate keys. So we could choose one of those to be a primary key, for example. A foreign key is an attribute or combination of attributes in one table whose values must either match the primary key in another table or be null. So it either has to exist or it has to match another table. So going back to that previous table, you can see that the vendor code in the vendor table is, the vendor code in the product table at the top is a foreign key that references the vendor code in the vendor table. Now, if there was no vendor or we didn't know who the vendor was, we could make the vendor code null in the product table. So it's not referencing anything in the other table. But what we couldn't do is reference a vendor that does not exist. So some integrity rules. We have entity integrity and referential integrity. With entity integrity, all primary key entries are unique and no part of a primary key may be null. We've already talked about that entity integrity rule. And then the referential integrity rule is, as we just discussed, you can never reference a foreign key can never reference something that doesn't exist in another table, where that primary key does not exist in the other table. So there are some ways to handle nulls. You could use flags to indicate the absence of a value or just an empty space or something like that. You could use a not null constraint, meaning that the user must provide a value. You could use a unique constraint. If you have a unique constraint, then you won't be able to have nulls because once there's more than one null, you violate that unique constraint. There's lots of reasons to not have nulls. We'll get into those later on, but just as a simple example, if you had, let's say, for example, in our table that we looked at, let's say you wanted to add or take let's say you wanted to do the average of all of the product prices, right? So we want to take the average price of all of our products. If one of them doesn't exist, if you multiply times nothing, what you end up with is nothing. If you add something to nothing, you end up with nothing. So nothing is kind of special mathematically. If you try to do anything with nothing, what you end up with is nothing. And that's why nulls can ruin your day. So it's generally a good idea for certain columns that you think you're going to be doing any kind of aggregation or mathematical operations or anything like that. You want to try to avoid null values. So again, there's a couple different ways to deal with those null values. Once we decide what these foreign keys are and these primary keys, one of the things we're able to do with the database engine is join these different tables together. And this is really important because to get meaningful use of our relational database, we have to join these tables together to get information from that database. So a join is the way we do that. There are different kinds of joins that your book talks about. For example, a natural join is when the join is automatic because, well, not necessarily automatic, but the table name or the foreign key and the primary key attributes have the same name, so the database engine is able to figure out how they're related to one another. You don't have to tell the database how to connect two different tables because it's a foreign and primary key relationship. It's already inherent in the database schema itself. There are also inner and outer joins. So an inner join is when we select from two different tables. So if we're trying to get information from two different tables, take for example, I keep going back to this diagram, but let's say we wanted to combine the vendor and the product into one result set. So let's say I wanted to show the name of a product and the vendor from which we purchased that product. Well, if I have a product that does not reference a vendor, then it won't show up. It's going to hide that product in my report. So that's an inner join. I'm only going to see products where there's a valid vendor. Likewise, if I'm looking at all my vendors and we have a product and we don't sell any products from one of the vendors, it's going to hide that vendor. We're not going to see it because there's no product that matches it. So that's an inner join. An outer join, on the other hand, allows us to show all of the vendors or all of the products. And you do that with, and I'll scroll forward here again. So that's where you would use a left or a right outer join. That's where you're telling the database engine which of the two tables you want to join to. So, or that you want to show all the records. Do I want to show all the vendors, even the ones that don't have products? Or do I want to show all the products, even the ones that don't have vendors? You can do either one or the other. So a data dictionary and a system catalog are sort of the metadata that describe how our database is structured. So a data dictionary describes all of the tables in the database created by the user and designer. And then the system catalog is the system data dictionary that describes all of the objects within the database. So this is the metadata that describes the data in the database, or the schema. I've talked about schemas before, and this is very similar to the schema. Homonyms and synonyms are a special case and something we have to be aware of when we're designing databases. When you think grammatically about homonyms and synonyms, what we're talking about are, so with homonyms, these are, grammatically a homonym is when two words sound similar or sound the same or are the same but mean something different. And a synonym is where you have two different words that mean the same thing. We want to avoid both of those in databases. We don't want to have the same terms describe different things in different tables. So we want to eliminate homonyms. We want to come up with a different term, right? So I'll give you an example. A common homonym that we see in databases is ID. A lot of people make up their own IDs. They might have a student ID, employee IDs, class IDs, and something like that. But instead of calling it a class ID, a student ID, and a professor ID or an employee ID, instead they just call them all ID. And then it becomes a homonym. It's the same term that means many different things. So we want to avoid that and make it a little less ambiguous. And likewise, we don't want to have different terms to describe the same thing. So we don't want to have different words that really mean the same thing. We want them all to be the same. Doesn't necessarily mean that you have to do this, but it's best practice to avoid homonyms and synonyms in a database design. So as far as how these objects relate to one another, there are three primary relationships we're going to see in our initial database designs and our logical designs of our databases. There's the most common, which is going to be the one-to-many relationship. So most of your tables in your design will probably be a one-to-many relationship. For example, a teacher has many students, a student can have many classes, and so forth. A one-to-one relationship is where an entity can relate it to one and only one, and vice versa. So for example, a husband can have a wife, and a wife can have a husband in most cases. A many-to-many relationship is where you can have many things on both sides of the relationship. And again, we'll see that later on the design. I will tell you that when we get to physical design, one of our jobs is going to be to eliminate those many-to-many relationships. We're also going to be doing that in database normalization. We'll see how to do that as well. So once you draw your crow's foot notation diagrams, you'll have your entities, and you'll connect them with lines, and you'll use those crow's foot notations to show the relationships. The way you read these, so for example, I would say that a student has, and then looking across to the class, I can see that a student has one or many classes, and a class has one or many students. Looking at the set at the bottom, I see that a student registers for one or many enrollments, and an enrollment has one and exactly one student. Likewise, an enrollment has one and only one class, and a class has one or many enrollments. So here you can see that database diagram in all put together, where the course has one or many classes, and a class can have one and only one course. A course can have one or many enrollments, an enrollment has one and only one class, and so forth and so on. So hopefully you're kind of getting a sense of how to read these, and then thus how to draw them. We'll talk about that in a little bit more detail next week. As far as redundancy goes, Relational Database facilitates control of data redundancies through the use of foreign keys. I talked about that already. Thinking back to the products and vendors, if we had many different products made by the same vendor, thinking back to that table, you can kind of imagine that you wouldn't have the vendor's name appearing over and over again in that table. Instead, you only have the reference. So if I needed to change the name of the vendor, I only have to change it in one place because it's referenced by all those other tables. If I didn't do that, if I had hundreds of products that are sold by the same vendor, if that vendor changed their name, I'd have to update hundreds of products. And what if I miss one of them or two of them or 9 of them, right? That could be a problem. And that could cause data integrity issues down the line as well. So it's important to try to avoid that redundancy. And that's one of the things that we're going to see how to do when we look at database normalization. I'm going to talk about indexes here just briefly. So indexes, and we'll see in our database designs later on, we're going to come back to indexing. But basically an index, when you think about a telephone book, in a telephone book, if you're looking up a phone number in a phone book, you don't start on page 1 and flip through page by page until you find someone's phone number. Instead, if you would use their last name, you would let's say your last name was Green, you would find the G's in the phone book and you would start there looking for Green. Because it's in alphabetical order, it's predictable and you can find that record. That's how databases work. Databases will use an index to try to find a record. Now the problem is, let's say in that phone book you were looking for someone's phone number, but you only knew their first name. So you wanted to look up all the records where the telephone subscriber's first name was Brian. Well, that's not listed in the phone book in alphabetical order by first name, it's by last name. So the only way you could do that would be to go through the phone book line by line. You would have to do a full scan of the entire phone book in order to find those records. And that's what a database engine has to do anytime you ask a database engine to find a record for which no index exists. So we can create indexes in our database on multiple fields. Unlike a phone book, which only has one index, which is the last name, our databases can have many indexes. Kind of like a textbook. In the back of your textbook, you have an index that you can look up which page numbers you can find the references to those indexes or to those terms. So database engines have to constantly keep those indexes up to date, and we'll see how that works later on. We'll talk about that and some of the concerns. So we certainly don't want an index on every possible field in our database, but we should choose wisely. We should choose the fields that we believe are going to be most commonly queried for in our database. So finally, in relational databases, there are 12 rules. These are Dr. Codd's, I'm sorry, not Dr. Boyce, Dr. Codd's 12 relational database rules. I'm not going to go through all of these rules line by line. We've already talked about most of these. So this is kind of the culmination of all of these concepts that we talked about in the relational model, kind of summed up in 12 rules. So I have all 12 of them here in the presentation, which you can certainly take a look at, and it's also in your textbook as well. And you can go through those rules, and you can certainly become familiar with those. I would recommend that you do so. We're going to come back to these rules. So throughout all of our database design decisions and all of our database design activities, we're going to make sure that we're complying with these 12 relational database rules. And in fact, if we follow a lot of the techniques that are talked about in our textbook and in this course, you're pretty much going to be in line with all of these rules if you do that, if you follow the guidelines and if you follow the best practices and normalization and so forth. So these are the 12 rules for COD's 12 rules rather, and again, it culminates everything we've talked about in this unit so far. So next week we're going to talk more detail about the ER diagrams and how to make those models, how to identify those entities and start relating them. And then later on we're going to get into how to do the physical design for our database, and then we're going to show how to convert that physical design into an actual database and how to create that code for our database, and then how to use database code to work with our databases. So that's the basic evolution of this class. If you have any questions, let me know. Thank you.